Okay, so hello everyone. In this video, we will cover virtual memory and page replacement algorithms. So in this video, first we will discuss about virtual memory, that how we will execute a bigger size process than the memory itself. Then we will discuss page replacement algorithm, in which we will see FIFO, LRU, MRU and optimal page replacement algorithm. And at last we will discuss thrashing concept. These are very important concepts, and we will see numerical question on these topics too. If we consider GATE, UGC NET or any kind of competitive exams, or even your college level exams, questions are mostly asked based on these topics. So let's move to the introduction to virtual memory. Virtual memory actually a concept that how we manage memory in computer system. Till now we have discussed a lot about the main memory, which is physical memory. In this lecture we will see how virtual memory actually works and what is the significance of virtual memory in modern operating system. The first and important significance of virtual memory is that it provides an illusion to the programmer that a process whose size is larger than the size of the main memory can also be executed. This means if I have a process whose size is even more than the size of main memory, we can execute that process as well. How is that possible? Let's understand this step by step. Our main memory is finite. If I talk about laptops, we typically get RAM up to like 8 GB or 16 GB. So if the main memory is 8 GB or 16 GB, but there are no limitation for size of processes. The size of processes is increasing day by day. Software applications are becoming more complex and memory intensive. So if a process whose size is more than the size of main memory needs to be executed, normally when a process won't fit in the main memory, how will we provide its progress or data to the CPU? This seems impossible, but virtual memory makes it possible. Virtual memory provides the illusion that processes whose size is much larger than the size of main memory can be executed. This is the first major advantage. The second point is related to degree of multiprogramming. In degree of multiprogramming, we talk about bringing more and more processes into the main memory simultaneously. We want maximum process to be available in main memory so that when one process goes for IO operation, another process can immediately start execution, keeping the CPU busy. Since main memory is limited, we need a strategy to bring the maximum number of processes into main memory. Normally we would need more main memory, but we have limited size of main memory, let's say 16 GB. So how will we bring maximum process in the memory and execute them efficiently? This is also an illusion provided by virtual memory. Now, how virtual memory works? So what we are doing here is utilizing the logical address space, which refers to hard disk where there are multiple processes stored. We have divided these processes into fixed size called pages. We have already seen the concept of paging, where we divide a process into pages and page size equal frame size in main memory. Now here is the key concept. Instead of bringing one full process into main memory, we are bringing only the required pages of the required process into main memory. We bring only those pages that are needed right now by CPU for execution. This approach is based on the simple but powerful concept locality of reference. What is the locality of reference? In locality of reference, when we bring a page into main memory, we don't bring that page alone. We bring related pages along with it. Let me give you a simple analogy. In a school class, when teacher is taking Viva, when a teacher calls roll number 10, what do we typically do? We might also call roll number 11 and 12 the nearby students, because we think that since roll number 10 was called now, next time the teacher might call roll number 9 or 11. This is exactly how locality of reference works in main memory management. Similarly, rather than bringing an entire process into main memory, we keep some pages of the process in main memory. In main memory, we can keep some pages of process P1, some pages of process P2 and some of P3 and some of P4 simultaneously. This means we don't bring the whole process into main memory. We keep only required pages that are currently needed. Since only some part of each process come into memory, we can keep parts of many processes in main memory simultaneously. The advantage is that parts of maximum number of processes can be kept in main memories. So when a user runs their computer, they think that whenever they call process 1, it's there, process 2, it's there. Many processes appear to be available in main memory, but these processes are not complete. Only some pages of each process are kept in main memory. We achieve this dynamic loading and unloading by using swap in or swap out operation. We also call it roll in or roll out. Swap in means we bring a page from the hard disk into main memory, and after some time, because we have limited main memory, we can't keep that page permanently in main memory. We will have to remove that page and bring some new process. This continuous process of replacing pages is called page replacement. Now moving forward to page fault and its handling. Now let's understand what happens when the CPU needs a page and that's not currently in the main memory. Let's say CPU is executing process P1. The CPU will make a demand for any page or data. Let's say CPU generates a demand for page number 1. How CPU will generate? Using logical address and MMU, memory management unit is mapping the logical address to physical address. So let's say CPU generates logical address of page number 1. It wants the data of page number 1. This means CPU generated a logical address, and from that logical address we determine that the data CPU is demanding located on page number 1 of process P1. Now the question here is, where is the page number 1 of process P1 in main memory? We check this using page table through the MMU, memory management unit. This memory management unit loads the page table from main memory and checks with the pages residing in which frames. When CPU demands data and the logical address indicates it wants P1 page, but if we look in the page table entry carefully, we might find that P1 page is not present in the main memory. In the page table entry, there are valid and invalid bits, also called present or absent bits. We have discussed it. That bits tells us that whether a page is currently present or absent in the main memory. If the page that CPU wants is absent in main memory, we call this situation a page fault. If the page is present, we can directly pick the page from the main memory and provide the required data to the CPU. But if that data is not in the main memory, it generates a page fault which needs to be handled by the operating system. Now let's see page fault service process. Exactly what happens during a page fault. When CPU generates a demand for page 1 of process P1, before accessing main memory, we first check the page table to see which frame the page is in. Now if we don't find any valid entry because the valid bit is 0 now, meaning the page is absent from the main memory, a trap is generated. A trap is a special kind of, we can say, interrupt that transfer control from user mode to kernel mode. As soon as the trap is generated, control transfer from user mode to operating system mode. This is essentially context switching. The user process that was executing is temporarily suspended and the operating system takes control to handle the page fault. Now, what does the operating system do when it gets control? First, it performs authentication and authorization checks. It verifies whether the user demanding this page is legitimate, has the right to access this particular page or not. This is done for security purposes to prevent unauthorized access to memory pages. If the user is valid and authorized, the operating system will proceed to provide the requested page. But where is the page located? The page is stored in the hard disk in what we call the logical address space or secondary storage. The operating system then searches the logical address space to locate the required page. Once the page is found on the hard disk, the operating system initiates an IO operation to bring page number 1 of process P1 from the hard disk into main memory. Let's say it places this page in frame number 7 of main memory. After the page is successfully loaded into main memory, the page table must be updated to reflect this change. Now the page table entry for page 1 is updated to show the page number 1 is now present in the frame number 7 and the valid bit is set to 1. Finally, after all these steps are completed, control is returned from the operating system back to the user process. This entire sequence of operation is called page fault service, and as you can imagine that this takes an considerable time compared to a normal memory access. Now, what is effective memory access time of this? We can calculate the effective memory access time using probability theory. This calculation helps us understand the performance impact of virtual memory systems. If the P is the probability that page fault occurs when CPU makes a memory request, then 1 minus P is the probability that the requested page is found in the main memory. The effective memory access time formula is P into page fault service time plus 1 minus P into main memory access time, where P is the probability of page fault occurring, 1 minus P is the probability of finding the page in the main memory, best case scenario. Page fault service time is the time taken to handle a page fault. Main memory access time is time taken to access data from RAM. When there is no page fault, probability is 1 minus P. We can access main memory directly, which typically takes a nanosecond because main memory is very fast. However, when a page fault occurs, the probability is P. The process is much more complex and time consuming. Page fault service time is generally measured in millisecond, while main memory access time is measured in nanosecond. Since 1 millisecond equal to 10 lakh nanoseconds, page fault can significantly increase the average memory access time. This is why the goal of any virtual memory system is to minimize page fault and maximize page hits for better overall system performance. Too many page faults can lead to a condition called thrashing, which we will discuss at last of this video. Now, moving forward to page replacement algorithms. When virtual memory is implemented, we never bring entire process into main memory at once. Instead, we maintain 1 or 2 pages of each process that currently in demand. Now, when the need for certain pages is over, we swap out those pages and swap in fresh pages that are now needed. The challenge arises when we want to bring a new page into main memory and all frames are already occupied. In this situation, we must remove an old page from main memory to make space for a new page. This is where page replacement algorithm becomes crucial. There are several page replacement algorithms, algorithm, but we will focus on three most common and important ones: first in, first out, FIFO, optimal page replacement, and least recently used, and MRU, most recently used. Each algorithm has its own strategy for deciding which page to remove when replacement is necessary. Now, moving forward to FIFO, first in, first out algorithm. In FIFO page replacement, we replace the frame like that was filled first, the oldest page in the memory. The logic is simple: the page that has been in memory the longest is the one that should be replaced first. Let's work through an detailed example to understand FIFO completely. Consider this reference string 701203042303. We have 3 frames available in main memory. Initially all frames are empty. When CPU demands page number 7, it's not present anywhere, so we get a page fault. We service this page fault and place page number 7 into frame number 1. Then CPU demands page number 0. Page number 0 is not present, page fault again, and we place page 0 in frame. Now all 3 frames are full. Next, page 2 is demanded. Page 2 is not present and we need to replace a page since all frames are full. According to FIFO, we replace the frame that was filled first. Frame 1 was filled first with page 7, so we replace that page number 7 with page number 2. We continue this process systematically. After replacing frame number 1, next we replace frame number 2, then frame number 3, then back to frame number 1, and so on. The replacement follows a circular pattern: frame number 1 to frame number 2, then frame number 3, then frame number 1, then frame number 2, and then frame number 3. Now, moving forward to optimal page replacement algorithm. The optimal page replacement algorithm provides the theoretical minimum number of page faults. In optical page replacement, whenever a page fault occurs, we replace the page that will not be used for the longest time in the future. The strategy is to look ahead in the reference string and determine which of the currently loaded pages will reference farthest in the future. Let's work through an example with reference string 7012030423 0321 2017 and 1, and with the 4 frames. Initially all frames are empty. Page 7, 0, 1 and 2 are loaded into the 4 frames, each causing a page fault since they are not initially present. When page 0 is requested next, it's already in the memory, page hit, and when page 3 is requested, it's not in the memory, so we need to replace an page. We look at the current page in the memory 7, 0, 1, 2. Looking forward in the reference string from this point, we check when each of these pages will be needed again. Page 0 appears when soon in the future references. Page 2 also appears relatively soon. Page 1 appears later. Page 7 appears much later in the sequence. Since page 7 will be needed farthest in the future, we will replace it with page number 3. The optimal algorithm continues this process for each page fault. Examine all pages currently in the memory. Look at in the reference string to see when each will be needed again and replace that one that will be needed farthest in the future or never needed again. While optimal replacement gives the minimum number of page faults theoretically, it's not practical for real system because we cannot predict future page references. However, it serves an benchmark for comparing other algorithms. Now, moving forward to LRU, least recently used method. LRU is based on the principle of temporary locality. If a page hasn't been used recently, it's less likely to be used in the near future. In LRU, we replace the page that was used least recently in the past. When a page fault occurs, we look backward in the time to see which of the current page in memory was referenced earlier, furthest in the past. That page becomes the candidate for replacement. Now, let's trace through the same reference string with LRU. This is the same string 70120 and so on. Initially, page 7, 0, 1 and 2 are loaded, causing 4 page fault. When page 0 is requested next, it's an hit. When page 3 is requested, we need to replace a page. Looking at the current pages 7, 0, 1, 2, we check which was used least recently. Page 0 was just referenced most recent. Page 2 was referenced when it was first loaded. Page 1 was referenced when it was first loaded. Page 7 was referenced when it was first loaded and it was the first among these. So we replace it with page 3. LRU generally performs better than FIFO because it considers the recency of page uses. However, LRU requires more overhead for tracking when each page was last used, which can be implemented through hardware support or software techniques. Now, moving forward to most recently used, MRU. MRU is the opposite of LRU. We replace the page that was used most recently. The logic behind MRU is that the page just accessed might not be needed again soon, so it's a good candidate for replacement. MRU can be effective in certain specific scenarios, particularly with sequential access pattern or certain database application. However, it's less commonly used than LRU because it often performs worse in typical computing environments. Now, moving forward to last important concept, thrashing. Thrashing is a critical performance problem directly linked with the degree of multiprogramming, the number of processes present in the RAM simultaneously. Understanding thrashing is essential for system performance optimization. The logic behind multiprogramming is straightforward. If we bring bring more process into RAM, it should increase CPU utilization. When one process block for IO operations, another process can immediately start execution, keeping the CPU busy and improving system throughput. Now, RAM size is limited and finite. To maximize multi-programming despite limited RAM, we use the paging technique. We divide process into pages and bring only necessary pages into RAM instead of entire process. This allows us to accommodate parts of many processes simultaneously. The problem here is when we try to maximize the degree of multi-programming beyond optimal levels. Consider this scenario. To accommodate maximum process, we bring only one page of each process into RAM. So we have page 1 of process P1, page 1 of process P2, page 1 of P3, and so on for 100 different processes. This strategy maximizes the degree of multi-programming. If CPU needs page number 1 of process P1, no problem, it's already in the memory. But what if CPU needs page 2 of process P1? Page 2 is not in the memory, causing the page fault. Similarly, if the CPU needs page 2 of process P2, page 3 of process P1, or any page other than page 1 of any process, we get page faults. Now, as the degree of multi-programming increase beyond the optimal point, we reach a situation where most CPU requests result in page faults. The system spends most of its time servicing the page faults. This creates a cycle. More page faults means more IO operation, which are extremely slow compared to memory operation. The CPU becomes idle waiting for disk operation to complete. Even though we have many processes in memory, the system performance degrades dramatically. The performance curve shows that as degree of multi-programming increases, CPU utilization initially increases, but beyond a critical point, let's call it lambda, CPU utilization suddenly drops due to excessive page faults. This sudden performance degradation is called thrashing. Now, how to prevent thrashing? There are two main approaches to prevent thrashing: increase memory size or control the degree of multi-programming. Now, if we increase main memory size, adding more RAM allows more pages to be kept in main memory simultaneously, reducing page faults. With more memory, we can maintain a higher degree of multi-programming without hitting the thrashing point. However, increasing memory size is not always practical. It is not cost effective. While it's a straightforward solution, it has limitation: hardware cost, physical constraints, power consumption, the fact that software demands tend to grow with available hardware. Now, the second suitable option is control the degree of multi-programming. A more sophisticated approach involves the using of long-term scheduler to intelligently control how many processes are brought into the ready state. The long-term scheduler is one of three types of schedulers in operating system: long-term, short-term, and medium-term. Its responsibility is to control the degree of multi-programming by deciding which process from the job queue should be brought into the ready queue in main memory. Instead of maximizing the degree of multi-programming to its absolute limit, we can configure the long-term scheduler to maintain its optimal level. Now, this optimal level provides enough process to keep the CPU busy when some process blocks for IO operations, but not so many processes that excessive page faults cause thrashing. The key is finding the right balance point, the degree of multi-programming that maximizes CPU utilization without triggering excessive page faults. This is the key. This requires monitoring system performance and dynamically adjusting the number of active processes based on current memory uses and page fault rates. Some modern operating system implement adaptive algorithm that monitor page faults rates and automatically adjust the degree of multi-programming. When page fault rates becomes too high, they temporarily reduce the number of active processes. When page fault rate decreases, they allow more processes to become active. So that was whole concept of thrashing, virtual memory, and all the algorithms. So that's it for this video. We will meet in next video. Until then, bye bye.